Okay, Paul here, and today we're going to be learning some assembly language, basically for Linux operating system. This code written is a server for a web server. So I called it the LX64 Assembly Web Server 1.0, LX course being Linux, x64 because it's with 64-bit architecture. We're going to go over the way it works. We'll actually write the code. Let me go ahead and show, before we go through the code, let me show you exactly what it does. Right now you see I have it ready to compile down here with NASM. And this would be normally 3 lines, but I just ended them together so I could do them all in one line. But basically the first thing it does is it creates the L64 object, the server.o, and then it compiles that to the server application, and then it launches the application with /server. So if I come here and hit enter, the server is now running. We see it as this little white square indicating that it's running. If I go to the browser here, just Chrome browser, and I type in start of the IP address, this is pre-filling because I've been doing this a lot, and you see I got a lot of crazy stuff going here that Google remembers. So we're going to go to it, runs on port 8080. This is my local PC. I'm not using localhost. I'm actually using my local IP on my Wi-Fi network. But it's the same PC we're recording this video. So when I come here, it presents the index.html, which is just a basic login box. Right? It's just to give you an idea of what we got. So if I come over here and select admin, that's the correct user ID. If I put in a incorrect password and hit login, it comes back, says login failed, try again. So if I go back and I put in the correct login, it takes me here. Of course, Google gives me a warning because it's not secure. It's running a web server on my local machine. But it generates this logged in, or displays my logged in.html form, which is just a table, you know, with some links that go to Google, GitHub, you know, just basic links. So, and of course NASM, which is, this is a NASM app, so this is a good page too. NASM.us, and it talks about how NASM compiles. Okay, there's also an alternate besides the login form and the displayed page when you successfully log in, and that's for APIs. So if I go to /API, it presents a JSON output of an API, and this is just an example, which we'll look at it in the code, but you know, it could be a business thing, right? The department is research and development, project has an ID, project 404, the name is the Apollo rewrite, and the deadline is December 31st, 2024. Employees, let's get the employee ID, 101, the name is Alice, the role is the lead. ID 102, the name is Bob, the role is Dev. So you get an idea. And this could be, you know, updated with, you know, current information, could be pulled from a database, could be really a lot of project IDs, not just this research and development project, but it's a JSON output, right? This is not pulled from a file. This is actually generated or displayed directly from the assembly. So we're going to look at that. So if I close the browser, we get back to the code here. I'm going to tell you a little bit about the application first. And we're going to break this down. We're going to build this in multiple videos where we go through actually how to create a web server that runs on your local machine. This will run on a laptop. It'll run on a PCP, a PC. Anyway, it runs locally. And of course, you could run it on your local host. I chose to run it on my actual IP address. It was easier, so I did that. But okay, this basic overview. The LX64 assembly web server is a direct system call based web server for Linux x86 64. Okay, it basically is what we call a system call based web server. So it sits there as a server, just like, you think of a web server, but it waits for system calls. So when you go to the browser and you go to the page, that generates a system call. The ASM processes the direct call. Now, the cool thing about this application is we are not using any Linux or Python, no libraries, no embedded anything. This is straight ASM, talking directly to the Linux kernel only. So this is talking right to the hardware and the Linux kernel. It's not using any libraries. There's no include statements. There's nothing being pulled down from the cloud. This works totally offline. It's directly connected to just your PC. No libraries, no C, no C++, no higher programming, DLLs like you would have in Windows, none of that. It's just straight assembly language, right? Basic computer programming as low as you can go in a Linux system. All right. How it works. There's a startup which creates a socket, and the socket is a connection socket to connect to the HTTP protocol. Okay. Then it binds to port 8080, which is hexadecimal IF90, or IF90, 90IF. But anyway, it creates a connection or binds to the port running on the server running on port 8080. And then it listens for a connection. There's an event loop that begins. It enters an accept loop where it waits for a client browser to connect. And you can connect with HTTP, you can connect with Firefox, or any other browser, or even Telnet, anything. You can just connect to it. If you can support HTTP protocol, you can connect to this with that application. Okay, so it's a standalone, fully functional web server from that standpoint. It has parsing, so when a connection request comes in, it reads it into a buffer and checks to see if it's an HTTP method of get or post. So is it a get request? Is it a post request? Those are the basic protocols for HTTP protocol request for internet, right? And then if it is, it also checks to see if it's what the path is. Is it index.html, the home page? Is it the login.html page after you're logged in? Is it an API you're requesting? So you can request a JSON API. You don't have to request HTTP. You can request JSON. It has file serving that when it gets a request, it sends it to a function or a routine called send full file full. And in that routine, if a file is requested, it opens the file. So if you're requesting a file like the homepage index.html, it opens the file on the hard drive, from the hard drive, reads it to get the exact size. So it reads it into a buffer, and it reads how many bytes of data are in that home page. It converts the sides to a string using a really cool subroutine called ITOA, which is integer to ASCII converter function. And then it sends the headers to the calling client along with the correct content length of what it's going to send out. So basically the browser says, hey, give me the home page. It goes, it opens the home page. It says, okay, here you go. I'm going to send you the home page. The home page is 785 bytes long. So then the browser sits there and waits until it gets 785 bytes, or whatever it is, right? You can change the size of the home page. It'll tell it the correct size to wait for. The browser will get the results and then display it, display the web page or the JSON file or whatever it is you're sending. Okay, so it does that, and it serves it that way. The application passes, if it's a JSON request, if it's an API request, then it goes to a label called check API, it's a block called check API, and the application passes the embedded JSON data. It doesn't open a file, it actually has it in the ASM. Right, in this code is an embedded JSON text. It reads that and it sends that to the client as JSON. That was the project data that we were just looking at. Okay. It uses an API versus HTML process to make that decision on what it's sending. You might ask, well, let's go through it and you'll see what's going on. First, we'll talk about the section data. This is the data section. This describes what options are available to the compiler. So this is what is available as data that can be sent via this application. So if you wanted to have it send like say about us page, you would have to edit this data section accordingly. Wouldn't have to do much to it, but you would change it a little. But we'll go through that. So looking at the data section, this is what, well, we covered this here. So looking at the data section, this is what we do. We have a file name, and this is just a variable called file name. Okay, and it has the value index.html, and it's terminated with a 0, a null string, because this is actually a file. So this is something, if you look at the files here, here's the index.html, here's the logged-in.html, okay, and then these are just some JSON control for my debugger, but they have nothing to do with the assembly. So those are the files that it sends. Well, the index.html is a file, so the way that assembly reads the HTML into this, it reads it and it has a 0 terminator to let it know when to stop reading the name of the file, basically. Success file is another variable. You can name these anything you want. They don't have to be these names. But success file is the logged-in.html. So when you log in, if you log in correctly, you get sent to this page. And again, it's read from the hard drive, so it has to be terminated and to know where to read the file. Then there are some string variables that are also used in the assembly code that we're going to look at. One is index path, index underscore path underscore string. This is the name of the URL. So when the server says, display the home page, it shows the home page. If you typed in /index HTML, it would compare that with this variable and say, okay, it's still the home page, and it would show you the same page. This line of code here, so these are file names on the hard drive, the actual names of the file. This is the file URL that you type in Chrome. And this line here with the minus in front of this is just a cool way in assembly language to calculate the number of characters in this line. So it counts these and it assigns it to this variable, into index path length. So when we want to serve this page, we have to tell it the length of this string, right? It's not like high-level language where you just tell it, here's a string variable. You got to actually specify to the CPU what the length of that string is, so it knows how long to read. Because remember, this is all in binary, right? In your memory on your PC, it's just ones and zeros, a whole long string. So the compiler or the CPU needs to know how many characters or bytes to read, and that's what this tells it. Because otherwise, it could overread, and that's a buffer overflow, or it could not read enough, and that'd be a buffer underflow. So anyway, that's what this is doing, okay? It calculates the length of the string. Here's another one. This is for the logged in HTML. Again, it's the URL that the browser asks for. Chrome says, send me the HTTP 10.0.0.1 on port 8080 / logged in HTML page. Well, that's what this variable holds, the name, / logged in HTML. And then the logged in length is, again, how many characters are in this name. And that's put into these variables so that they can be used by the assembler, by the assembly code. Now this one is for HTTP header. So when the browser says, give me the home page, index HTML, you have to send a header first, then you send the file, and then you send the end of the header, which is this line here. So when you send the header, you have to tell the browser this is HTTP /1.1, which is the protocol name. This is the protocol version of HTTP that the server is sending to the browser. It's the current version. 200 OK just tells the browser that I got your request and this is the response. 200 is correct response. 404 would mean file not found, right? But this is, the file was definitely found, and so it sends 200 and everything's okay. And then this 1315, these are the terminators for this particular line. So this is basically an old programming language like VB script and stuff like that. You would say carriage return line feed. Well, that comes from the old typewriter days, right? So a line feed is moving in an old typewriter, manual typewriter. That means moving to the beginning of the line. Well, if you type this and then you move to the beginning of the line and you start typing again on an old typewriter, you're typing over what was already there. So when they first went to computers, they were using terminal types. Well, first they used punch cards and punch tape, but then they started using terminals to send code to the processor. So they adopted the old way that an old typewriter, manual typewriter would work. And the way an old typewriter would work is when you pushed the lever to go back to the page, it would not only go to the beginning of the file, but it would turn the wheel up one notch so that you'd be on the next line. So that was called a line feed. So the carriage return would return the carriage to the beginning of where you would start typing again, and the line feed would click it up a line so you're not typing over what you already typed. So they held that onto that, and it's in programming. It's in all the protocols used today in communication. We still use 13 and 10. These are the byte codes for carriage return line feed, as you can see here. So we send those for HTTP header lines. We send that each time. Now content length, you notice, doesn't have it. And that's because we haven't calculated what the length is yet. That's what we have a response, actually, that does that when it reads the data from the hard drive. When it reads the file, it calculates how long that is. And when it calculates how long that is, it puts it in here right after this space. It literally writes it into this line, and the closing of the header sends two carriage return line feeds. Sends one saying for this, saying it's done, and then it sends another one for a new line, because it has to be a space between the header and the body of the web page. Okay, so that's what's happening here. And you can, if you was writing ASM and you're new, and you're writing something like this, you'd get some assistance from a book or someone who's a higher level programmer, right? Or you could ask AI if you got the guts to trust the AI, and it'll explain that to you. But basically, that's what's going on here. So the header, and so you got the header that's sent to the browser, then you got the web page that's sent to the browser, and then you got the you get the header sent to the browser, then you get the end of the header command sent to the browser, and then you get the web page sent to the browser. And that way the browser knows, okay, knows all about it, right? Knows it's text-based HTML document. It's coming in as an HTTP protocol. It's coming in through a connection that will be closed. So this tells tells Chrome, right? The ASM here tells Chrome, I'm going to send you this file. It's going to come in as text. It's going to come in by the HTTP protocol, and then I'm closing the connection. I'm not going to leave this connection open. I'm just closing it. So once you get this, that's it. There's nothing else to come. So that's what connection close tells the browser. And then it sends, when it puts the length in here, it includes the length of the file as well as the length of the header, as well as the length of basically the whole buffer. It says, this is what you're going to get, this many bytes. Then it closes the connection, and that's it. It sent it back. The browser asked for the home page. It gave it a header information, telling it all about the sides of the home page, sent the home page, told it the format that it's sending in, and then it says, I'm closing the connection. There's your home page. Okay? And that's all that this section does. Now, down here, if you ask for an API, then it's going to send a different protocol. It's still going to send it over the HTTP protocol because it's a web browser, right? It's Chrome or, Firefox that's asking for it. So you got to send it back in the same protocol that uses, which is HTTP 1.1. But the content type's different. It's no longer text HTML document. It's not an HTML web page. Instead, it's a JSON formatted data stream. So it's what we're saying as API. It's basically JSON formatted data. And then the same thing, I'm going to send you this, and it's going to be this long, and I'm going to close the connection. and wham, there's the response to Firefox or Chrome. Okay, so this is all in the data section. This basically defines how the data is communicated back and forth. Now, when you log in, you get the login form, you put in the username and the password. The assembly language checks it. If it's correct, then it's going to send a response, a 303 code, which means go to this. It's a 200, it's sort of like 200. It's saying it's okay, but it's not in the same place. It's at a different place, and that different place is here. Now this could be /API/version2/loggedin.html. Could be anywhere. So this just tells the browser where it is. It's over here. Okay, because the browser didn't ask for this. It just asked to check and see if the login information is right. So this is coming back and saying, yeah, it's okay, it's fine, but the file you want is really over here. And so then the browser calls that file like it does up here, and the file is given back to it again. So this just tells the browser, hey, look over here. In other words, basically the username and the password were correct. I'm satisfied, so you got my permission to go look at this file. That's what the web service pretty much saying. And again, I'm going to close the connection, and here it is. And it sends the file over. Now, that defines these variables which manage that communication, right? The next thing is this section here. And here, we're talking about the API. And this is, as you can see, is the department stuff that we had when we typed in API in the browser. It said department, research and development, blah, 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 file rewrite, the deadline, and the name of the lead and the developer involved in the project. And again, this could be multiple lines. Okay, first question that's obvious is, why are we doing this like this? Why is it not just a text file on the hard drive, like the home page and the logged in page that we just read a API.json file and send it? The reason we're doing it this way in the code is not because it has to be done this way. It really would be done as a text file. But this is just to show that you can actually write data, actually hard code data in the ASM file, and then send that data as though it was from an actual file on the hard drive. Of course, that's a lot faster, right? It doesn't need to read and write from the hard drive. It's already got it right here. So it just sends it. And so we created a variable called API body, which is sort of like the text documents that we're reading off the hard drive. And we're saying that we're just, instead of reading it from the hard drive and putting it in API body, we're writing it directly into API body with these lines of codes and these DB commands, double byte for each one of these as it writes each line into the code. Now, you may ask why, or may have noticed something different between these two, and that is the carriage return line feed in HTML. But here, where we're sending JSON, all we have is line feeds. We don't have any carriage returns, right? We're not sending it. Why is that? Well, that would be a good question to ask. And it has to do with the protocols. This is HTTP protocol for web pages. This is JSON protocol for JSON. It's totally different, and they function differently. So to give you an answer, here's a breakdown of why we used just 10 here, which is equivalent to /n in a lot of programming languages like Python and C and other languages. We're just sending a new line feed. Go down to the next line, go down to the next line, go down to the next line. No carriage return line feed, no carriage return needed. So there's no, it's not the same as above where you would have /r/n. Carriage return, new line, or carriage return line feed. It's not the same. Here it's just /n. The difference is HTTP headers, like the one we were looking at up here, have a strict carriage return line feed requirement. The HTTP specification, which is RFC 7230, that's the specification, RFC 7230, it strictly requires the header lines end with the line feed, carriage return, and the line feed. However, in JSON, it uses a different protocol that doesn't require that. And so it just needs the line feed, and that is RFC 8259. And you can put carriage return line feed here if you want. You don't even need to put anything here, according to RFC 8259. It automatically knows that each line is an individual line. That's part of how JSON works, right? And actually, they don't need to be any line feeds. This is for readability, so that when we look at the page in Chrome or wherever, we can see it formatted, laying out this way, right? But if we send it without the 10, it would just be one long line, because JSON is formatted by open and close curly brackets, right? And embedded curly brackets here, where you got embedded inside of the employee one, which is a block or an array, you got an array of 2 embedded JSON lines or more. So it could be just one long line. Well, that'd be hard to read. So we put in a line 10, which is a new line character, just so that it breaks it down like this, so it's easier to read. But it's not required. And most JSON parsing applications would automatically handle it no matter how you do it. Whether you put the carriage return or not, doesn't matter. But for our demonstration, I wanted to explain the difference between HTTP, which requires both, and JSON doesn't. So I guess I killed that horse, but let's continue. Okay, now we have 2 more variables, admin user and admin password, or admin pass. And we're hard coding the correct user ID and password right here. We don't have to do that. It could be in a database, it could be on a file on a hard drive that's not accessible by the world. I mean, it could be encrypted somewhere. But just for simplicity of the code, so you understand what's happening, I just chose to hard code it here. And we don't want to make this any more complicated than it has to be. The idea is to learn what's going on. And so this is irrelevant, right? It could be done a lot of different ways. So could this. It could be from a database. So could the web pages. They could be pulled pieces from different tables in a database and put together to make a web page on the fly. It doesn't have to be an actual file. So, I mean, there's a lot of different ways to do this, but I'm trying to cover different options so you can see different approaches to handling data, basically. Okay, then we got 2 other variables. One is login failed message, which says login failed, please try again. Again, that could be from a file. It doesn't have to be hard-coded. Why not hard-code it, right? And login file fail length, this is the length of this statement. Have to tell the browser or ASM just how long that is in memory, or it doesn't know what to read and how long to read it. Remember, it's computer language. The CPU can't read. It just counts bytes and returns the value of all those bytes. So you got to tell it where to start and where to end. Could be an offset. you might just tell it, start at, position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You might tell it, write out at offset 16 the rest of the characters, and it would just put this break, please try again, break. So, this tells it how long it is, and you could even use an offset to say, hey, start over here, start with T, try again. I mean, you could do whatever you want, right? So having those in the variables here, you got something to work with. It starts at 0, it ends at this, which would be here. Okay, then we come to something that's a little bit more interesting, and this is actually how the IP address that this server is running on is set up. So we got a double word, which is 2 bytes, and that 2 bytes is this. This is 90IF. This tells the CPU that this server is running on port 8080, okay? Port 8080 is IF90, but the way it's stored in memory is by what they call Little Indian storage. So if it went in this way into storage, then the first byte that was written is this one, and the second byte that was written is this one. So it's written first as 90 and second as IF. And of course, that's the way it's going to be read and sent to the communicating protocol, the network adapter, right? It's going to be sent in the reverse order because it's written in the reverse order in memory. It has to be switched back, and so this is the way it's handled to switch it back. It's in reverse order, the 2 bytes in reverse order. That happens over and over. It's going to be a point of confusion for you as you write in ASM. You're going to have to remember what has to be in reverse order and what can be in normal order like this. This is the actual IP address, 10.0.0.11. So in this format, we're telling it specifically it's 10, 0, 0, 11. If we were going to write it all out as dots, 10.0.0.11, it would be written backwards in memory and we would have to switch it. So this is just a good notation to write it forward. But you can't send this to a network adapter. It doesn't understand commas. It expects periods. So you can't do that. So this is a shorthand notation that the assembly language will handle when it's sending it to the network card or to your Wi-Fi, as it'll convert it to the correct format. But the network card is low-level programming. You're right down to the actual bits and bytes of the network card. And so for the port number, it's got to be written backwards in memory, and it's going to come out that way. Just realize that if you had this backwards, this would be like port 38,000 and something, So if you had it written the actual way, 1F90. So just realize that there are times when bytes have to be written in reverse order. Think of it this way. When you see OX, it's pretty much this was the first thing written, this was the second thing written, and if this was, 10 bytes long, it would be 10 bytes written in the reverse order. So just keep that in mind. Okay, here we have another 2 variables for 404 error. So when, again, this is HTTP, so when the browser says, hey, send me jackthерipper.html, and there is no such file, then the program sends back this header information that says, this is the protocol, I'm sending you this data, the file doesn't exist. And it's text HTML you was looking for, but there is no file in that format. I'm closing the connection, goodbye, and it closes the connection. Now we come to a little bit more interesting. You can think of this as all metadata and how the two devices or the two applications, the browser and the server, how they communicate. This is how they communicate. This is the protocol formats that they use. Now we're looking at what's called the .bss section. This is global variables. So these variables are not like these variables. This is communication protocol. This is actually variables for your application. You can put as many in here as you want. And so let's take a look at what's going on here. And in this .bss section, you can have as many variables. Think of them as global. If you write programs in any other language, you know you have global variables and you have local scope variables. Local variables would be variables that are in a function or sub-function or something like that, or in a, they're just local to a particular scope, like in a loop. You might have counters defined that only exist while that loop is going on. Those are local functions. This is global. You can also think of these as global variables that don't change, right? They're always the same. In this case, they're not always the same, but you could put some in here that do not change. You could put a variable that has a value and it's global. It'll always have that value. Okay. So here we got a client FD, or a client connection string. This is the connection ID. It takes up 1 byte because you can't have more than one connection at a time. So 1 byte is plenty. That gives you up 00 to 99. I mean, that's a lot of potential. But anyway, that's the idea of the client connection. That's what's being assigned to this variable. So once you make a connection, it gets a connection ID. You use that all through your application. That's always the connection you're going to use, because that's the connection that was assigned to you when you create the connection string. And then the request buffer is communication. That's this stuff that's going back and forth. We're setting it at 1024 bytes. So we're reserving 1024 bytes for data coming in. And so back and forth, right? This is the bytes for a buffer that is reserved. We're reserving that amount of memory for a buffer. And that's JSON. And since we hard-coded it in here, we know it ain't over 1,000 bytes. It's not even half that. So this is fine, right? We're saying this is great. So we could add more here and it would still fit in 1024 bytes. For the HTML pages, now that's different. We might have really long HTML pages, and you can change these to whatever you want. So for HTML, we're setting it to 8192 bytes. So that's the buffer to hold the HTML content. The files we read off the hard drive are read into this buffer. Okay, and so these are variables. So whenever we want to point to the HTML page that we read, we would use this buffer, which is a pointer to that block of 8192. And it's that size. So basically it's an integer of 8192, but it's reserved in memory and it's assigned a buffer location. It's assigned a memory location in RAM, and it's that long. That's what basically you're asking the compiler or the CPU, hey, I need a place to store some data. I need a place that will store 8192 bytes of data. Okay, so the CPU says, okay, we'll reserve this section for you. And then that section has a pointer or a location start. And then it's 8192 bytes long. And then the ITOA, integer to ASCII buffer, also needs a buffer to work with. It's going to be switching characters around. So it needed some area in RAM to do that, to calculate what it needs to calculate. And so we're reserving, and that's what RES means, reserve bytes. We're reserving 16 bytes for that. So the CPU says, okay, well, here we'll use these 16 bytes to hold this guy's data, right? That's what's going on there. Then we come to the actual application itself, and that's under the section.txt. So these set up everything. This sets up the data that we're using. This sets up the variables that we're going to use to communicate with our application, and then this is the application. And you notice that the first thing is a global variable set up called start. That's a memory location where the CPU knows, okay, this is where the application starts in RAM. This is where it resides. That's where all this code sits. It sits in at that position in RAM. And so this is the flag that says, okay, what I want you to write in this global start variable in RAM is these lines of code. And this is where it puts this code. It's not actually doing the code, it's writing this program down in RAM. Okay? So the next thing that happens is we start having blocks. And you can think of these blocks down to a system call like this as a block or a command section, right? This is like a command. This is like telling your kid, hey, go wash the dishes. Or I want you to take out the trash. While you're taking out the trash, check the mail. And when you finish check the mail, come back in and let me know it's done. Okay, it's a series of commands and then a series of setup steps or steps, things, tasks you got to do, and this is the command, go do it. Okay, syscall is the command, hey, kernel, go do this. Okay, so what does it do? Well, the first thing we do is we create a socket. Now, if you're learning ASM and you haven't learned the basics about registries, you need to go and pause this video or stop this video and go do a search on Google or something about x64 registries, how they work, about the stack, how it works. We'll talk a little bit about it as we go along, but this is an advanced program. This is not something that we can cover all of this stuff on the fly as we're going through it. We'll just confuse you. You got to have a basic understanding of ASM, because this is, we're writing an actual application that's running without any libraries, right? Without any embedded code from anybody else. There's no repositories being pulled down from Git in the background or GitHub. This is actual local code. We're telling the computer exactly what to do, line by line. Okay? So keep that in mind. So you got to know that. But there are, just to give you an idea, there are high-level there are registries in the CPU. There are registries, little places of memory on the actual processor chip that hold CPU data while it's processing, right? And that's where everything happens. These are not RAM locations. These are actually bytes of data on the 8-byte chunks of data running on the processor chip itself. That's where the CPU gets its commands and where it writes its results into these registries. So just bear in mind, some of them are very volatile. In other words, they're read and written to so often that you got to be careful what you do with them. RAX is one. RAX is a primary one. It's used all of the time. You see it everywhere down here. And I don't think you will ever see a system call that doesn't do something with RAX. And it also is where you get the result. When the system call is finished, it responds with a response, and that response is usually in RAX. So RAX is an important registry. Nothing wrong with using it. We're assigning it a value right here. When you see the word move in assembly, you can think copy, because that's what we're doing. We're copying into RAX the value here, 41. 41 is the socket stream value. That's what we're setting up. We're trying to create an internet socket to listen on the internet, to communicate on the internet. So to communicate over the network, right? So we send in, we set RAX to 41, which is basically telling the CPU, we want to create a socket. That's what 41 is. And if you want to do a Google search, you can search on this. It's a little more technical, tell you exactly how we do this. But we're looking at it right here. It's a socket function command. It takes in 3 values. Takes in an INET, internet, AF internet value, a socket stream value, and a terminating 0. Okay, so those all come in, and that's what the 41 is. It includes that. To do that, to put in these variables, we're setting, so basically this is telling the CPU, this is what we're going to do. And then the CPU is like, okay, that's fine, but I need to know what the AF INET is. Well, that goes into RDI. So we set it to 2, because that's the Internet protocol that we're using. We're using Internet Protocol 2. I don't know exactly what that means. I don't really care. I just know this is how you set up a socket, okay? So just keep that in mind. This is the required information that we got to send in. Well, we'll see how that works in a minute. So there's the first parameter. First we say we're going to set up a socket. The first parameter is going to be 2. It'll be written in the registry RDI. The CPU knows to look in RDI to find the first variable, right? Or first parameter. Then in RSI, we're setting a 1. That's the socket stream. So we're telling the CPU we're going to use RSI for the socket stream. The CPU already knows that it's going to be in RSI. It's going to want to know what is it that's in RSI. 1 tells it that's the socket stream parameter. Okay. Then we need to send a 0. The CPU knows that the 0 is going to be in EDX. So we could say move, actually it's going to look in RDX. We could put move RDX, comma 0, which would be the null terminator string. But that takes a few more bytes than saying XOR RDX, RDX. If we said XOR RDX, RDX, that would basically make RDX 0. But you're thinking to yourself, well, Paul, what about EDX? Well, EDX is the lower half of RDX. EDX is the lower bytes of RDX register. I think EDX is 4 bytes and RDX is 8 bytes. Not exactly sure. I don't really remember. But rather than saying, an XOR basically just makes them 0. That's all it does. This or this. Well, they're the same, so the result is 0. But rather than saying RDX, which takes 3 bytes in the process, in ASM, bytes are important. The more bytes you use, the more computer time you're using. So you want to cut the bytes down as much as you can. we're saying take the bottom half, or the bottom 8 bytes, actually, yeah, I think it's 8. But anyway, I'm not sure on this particular register. Take the bottom bytes and set them to 0. When you do that, the top bytes are automatically set to 0. So setting EDX to 0 automatically sets RDX to 0, because the CPU automatically zeroes out the top bytes when it sets the bottom bytes to all zeros. So the whole thing becomes zeros, but it uses a lot less than saying move RDX 0. We just saved a lot. So that's why when you see XOR, and the same thing on both sides, when you see XOR, all you're doing is setting that to 0. Okay, so that's what we're doing here. That's the 0. So there's the command. We're going to send, we need a socket. We want a INET in RDI, and we want the socket stream in RSI, and we want, we're putting a 0 in EDX. And then we call the system call. When that happens, the system call hands this over to the Linux kernel. The Linux kernel gets the socket information and sends it back into RDX. So that's why I said RAX rather. RAX is used all the time. So what comes out of here is this socket connection with all this information that was assigned by the Linux kernel is thrown into RAX. Well, because RAX changes constantly, it's always changing, it's in all of the blocks, we don't want it to stay in RAX. It's only going to be overwritten if it does. So we move, or copy, right, move it into a different register. We stick it in R12. R12 is a safe register to use. In fact, it won't be overwritten in R12 pretty much unless we write it in something over it in R12. So it'll stay there. Then the next thing we do, after we do that, here we could do this another way. We could put this line first, but for the sake of flow, we got it here. This is considering it works, right? So bam, it's good. It's thrown in RAX. Now R12. Now in R12 we have all our socket information, so we can communicate with the outside world. It all lives, all the connection information lives in R12, ready to be used anytime we want to use it. Okay? So keep that in mind. Then, since we know that it's still in RAX, we're going to compare RAX to 0. And all this does is it sets a flag in another register, in a pointer register, or a flags register. It sets 1 bit, the 0 bit. It'll set it to 1 if RAX is equal to 0. It compares these two. If they're the same, it sets that flag bit to 1. If they're not the same, it sets it to 0. So it compares RAX with 0. And 0, in computer memory, you can think of as 0 as false, 1 is true. So if RAX equals 0, it sets it to true. If RAX doesn't equal 0, it sets it to 0, false. So then it says here, jump less than. If that flag is less than equal, they're not equal. They are equal. If that flag is equal to 0, right? If it's 0, then we didn't get a connection. When this command went through Linux kernel, it returned a 0 rather than all of this. So if it set this to 0, that means there was an error. Something went wrong. So we jump to exit error socket. We jump to this location that says, hey, we didn't get a connection. No sense going any further. We can't communicate if we don't have a connection. But that's not normally the case, right? Normally this works fine, no problem, bam. This does not equal 0. So we keep going. So we don't leave. There's no error. The next thing we need to do now that we got a connection string that was assigned to us, we have to connect to it. We need to bind to that string. So basically, this says to Linux, hey, I need a connection. This is sort of like I don't know if you've seen videos of the old days of switchboard operators, when you would call the operator and say, I want to talk to the drugstore down the street, Jay's Drugs. The operator would stick a plug in your phone, one end of a cable in your phone connection, and stick the other end in Jay's Drugs connection, and you're now connected by that line, by that cable. And so you could talk to them, they could talk to you, and then you could hang up and the operator would pull that cable out. Later on in phones, that was done automated. They didn't need a system operator anymore to plug one end of the cable in one, and it's all automated, right? So, but it's the same process. So here the Linux said, okay, I made a connection for you, an outgoing connection on port 80, and here it is. Here's the other end. Plug it in wherever you want to plug it in. Okay, my end's plugged in. You're ready to connect to the outside world, but you got to plug your end in somewhere, and that's called binding the socket to an address. So we're going to bind that socket, which we got in R12 because we moved it into R12. We're going to move it into RDI. We're going to get the address, the relative address of where this is, and we're going to move that into RSI, and that's calculated by the current location of the current instruction pointer. There's an instruction pointer going down the memory location as we work in the stack or wherever in RAM. So we got an instruction pointer that's pointing to R12. So we move the address of that pointer of this R12, where R12 starts, where this S is, right, in a sense, where it starts. We move that into RSI. We move 16 into RDX because it's a 16-byte long connection. We move 49 into RAX because, again, RAX carries commands. So we're telling it we want to bind this server response, this address, and this number of bytes. We want to plug that cable in. We want to bind our socket. And that's what this system call will do. So then we call a system call. Linux kernel looks at these and says, okay, we're going to plug the other end of the cable in here. And so now it returns, and Rx has the value of that connection on our side. So the connection on the socket has been made, and now we got the other end of the cable from the operator, and we plugged it in, and it's plugged in. The next thing we got to do is, again, sort of like we did here, compare RAX to 0, we're doing the same thing again. Is it connected? If it's 0, then the binding failed, and we got to jump again, error bind. If it's not 0, then we got a valid connection. We don't care what it is. We just know we got a valid connection in RAX. So we just leave it alone. We've been bound. Now, you see what I mean by RAX has changed? Before it had the value of this string. We threw it in R12 as a holding cell and said, hey, this is a copy. We'll keep it there. We'll always know what it is because it'll always be written on our notepad in R12. Now, when we do this system call, RAX has changed. This is no longer in RAX. What's in there now is the binding address. Okay, so we check it. Yes, it's good. We don't care what it is. We just leave it alone. We don't try to write it down. We don't copy it into another register like we did here. We just ignore it. It's going to be overwritten anyway. We just want to know that, hey, we were connected. Were we successfully connected? Yes. Good. Let's continue. And that's what the code is doing here. So I hope you're seeing how this works, how it falls through, right? Now we're going to listen for connections. So we need to tell the Linux kernel that, okay, we plugged it in on our side, you plugged it in on your side. Now we need to know when somebody starts talking in this connection. Someone wants to talk to us, ask us a question, we need to know when. So basically we move R12, the connection string, into RDI. We copy it into RDI. It's always in R12. We'll leave it there. We're just copying it into RDI. We copy 5 into RSI. Forget why we copy 5. I don't know what that means. 5. It's the server listening command. And we copy that command into RAX. And so basically we're telling Linux here, hey, we put a connection string here in RDI, and we want to listen on that line. And then we send a system call. And of course, RAX gets the answer back. But at this point, we already know everything's working fine, so we don't even need to check RAX. It's going to come back with a response. But the point is, we did a system call. We said, hey, we want to listen. Turn on the volume. Turn up the volume so we can hear when somebody's talking to us on this line. Okay? Then we enter, and I'm going to stop right here, and we'll do another video because this video is getting long. But at this point, after we got the connection and we can hear somebody calling to us saying, hey, you, I need the home page. We can hear that. So the next thing we need to do is accept it. So when the phone rings, somebody calls us and the phone's ringing, right? We got to answer it. That's this accept loop. This is not just accepting it. This is not just answering it, but it's what do we do? We accept the call. It's from the IRS. They want us to go to a meeting to audit us. We need to go, right? Or we accept the call and, it's some other request and we got to go do that request. So this is a loop. Anytime anybody calls, we loop through until we finish doing whatever it is that we have to do based on that connection. So the first thing we need to do is pick up the phone. Somebody's calling us, we got to pick up the phone and answer it. So we move, again, the connection string from R12 back into RDI again because it's been overwritten. And then we set RSI to 0 because that's what needs to be in there. We set RDX to 0. And I'm saying R, but you can see that this is E and E, right? This is the lower half of R. So whenever you see E, you know it's half of R. So the RSI is twice as big as ESI. But we don't need to use up those extra bytes by XORing RSI and RSI. We can just XOR the bottom half. ESI and ESI, same thing. If you got a bag of Skittles and you want to empty it, you could dump the whole bag, right? Or you could take a razor knife, cut off the bottom half of the bag and everything falls out. It's still 0. But, if the top end is wire tied and you got to go and untwist it and take time to untwist it to dump the bag out, it's easier just to pop a hole in the bottom and let it drain out. That's exactly what this does. We're just draining our RSI to 0 to empty really fast. You can think of it that way. Now, these values, and then we send in a 43 command into RAX. This tells the system call, the Linux kernel, we want to accept this call. Somebody just called us. We want to pick up the phone. That's this command. Okay, but why do we set these to 0? Well, there's a reason. The first one is the pointer of the IP address of the caller, or the telephone number of the caller. That's what's in what would go into ESI. But if we don't care who the caller is, we're not going to even bother looking at the phone number on our phone to see who's calling us. If we don't really care, then we put in a 0, which means ignore. Ignore the IP address. Don't waste time writing that down in memory and waste space. We don't care who's calling. We're just answering the phone. The second one, EDX, if we did care about who's calling us, then we need to know how long is their phone number. Is it an international call with a whole lot of numbers, or is it a short call locally? Or is it a text message that's just four numbers, right? We need to know how long that address is so we can write it to memory. Well, obviously, if we're ignoring it, we don't care how long it is. So we set that to 0, and that ignores that too. All we want to do is accept the call. So when we do this, the operator connects us, and the call is coming through. We get the call. This is where everything begins. Now, when that happens, we're given in our AX the actual connection, right? The phone was answered, the other person speaking. That's happening on this client location. So we record that conversation start on this connection, on this protocol connection string. So it goes into our global variable. Now, anytime we say something, anytime they say something, it's over this phone line. And so this is the phone line that handles that connection. You see it in other places. We no longer have to do this. We've already answered the phone. We already know who they are, and if we cared, we got their info, but we didn't care about that. We just wanted the connection. We got the connection. We can use it constantly. It's in this variable that we created up above. So we got the connection. We have the buffer. So we know we got a request buffer. That's where the data, when they speak to us, think of it as an answering machine. We accepted the call, or our phone accepted the call, our phone service, and I'm sorry, they're not available right now. Please leave your name and number at the beep. Beep! The name and number goes in this buffer. So whatever they had to say is recorded here. Up to 1024. If they're long-winded and they talk for this length of amount of characters of text or words, they're shut off. That's it. Anything else they say, click. We already hung up at 1024. So we don't have to worry about getting a message that's too long for us to listen to and takes up all of our answering machine, so that we run out of room and the next person calls and it says, "We're sorry, they're not available. Please leave a name and number at the beep." Beep! "We're sorry, this person's mailbox is full." We don't want our next customer to get that. So this stops it, right? You get the idea. Okay. So now we have the phone call message. We're going to answer the phone call. We're going to call them back and give them the answer to that message. Okay, so we're going to stop right here, and we're going to pick up with this on the next video as to what is this? What did they ask for, and how do we give it to them? Okay, take some time and review this and try to get an understanding on what's happening here. And remember, the reason that this is a loop is because they ask, you get a phone call from your mother, "Hey, how you doing today?" And then you respond, "Oh, I'm okay, how about you?" And then they come back into the top of the loop, "I'm okay, my arthritis is acting up a little." "Oh, did you see your doctor?" We respond back, "I got an appointment next month on the 15th. I'm taking some ibuprofen for the pain." "Oh, good. Well, I'm glad to hear that you got an appointment with your doctor. Things are okay over here." You see what I mean? It's a loop of conversation because the phone is connected. right? That's what's going on here, okay? So keep that in mind, and we'll come back to this in the next video. Hope you found this interesting. If you want to continue this process and learn more about assembly language and how it works, and maybe build out this server and have your own private web server, you can do that. And just subscribe and like, and we'll get back with you. And when we get to the next one, you'll get a notification. Thanks for watching. Have a great day.